There we go.
Sick. So, okay, so now we have two images, right? We have this image that when you look at what the pixel values are, the pixel values are 0, 0.5, 1, and 0. You have a second image that when you look at the pixel values, there's 1, 0, 0, 1. Now what you can do is you can vectorize this one too, and then organize. You can organize everything like this. 0, 0.5, 1, 0, and 1,
0, 1, or 0, 1.
Yep, exactly. And this is pixel 1, pixel 2,
Pixel 3, and Pixel 4.
1.
Got you.
Pix
Interesting.
2, Pix 3, and pixel 4. Now this thing is organized exactly the same way that this thing is, except instead of longitude, latitude, and price, it's the pixels or the columns now, right? And so the pixels are now the features of all of your images.
And this is the base for how Stable Diffusion, DALL-E, and kind of
all the image-based stuff. They all do this. Like that's how you organize all of your data. Is you unwrap all of your images, you stick them as rows on a data matrix.
Yeah.
Over here, same shit, right? This gets a little bit more confusing, but this one is going to have columns too. With text, it's a little bit harder to interpret the columns because with text, the columns for each word were sort of invented by saying, if we view this stuff geometrically, related words are close to each other in geometric space, and unrelated words are far away from those. Right. And so, like, the columns of this are axes of that space, but they don't necessarily, like, it's not something like just like longitude or latitude, right? Like they're sort of just numbers, but when combined together, those numbers mean something interesting.
Yeah.
So I'm gonna leave this here because we're gonna come back to understanding this. So I'm gonna erase all this. You have all this in your head?
Yeah.
So let's talk through it for a second. So explain to me what's going on over here and how these are related and everything.
The way that we're actually dictating the data with the actual vector sets is that so image data and tab data are pretty much can be compared in the same way. You can either do it based off of a rows or cols setup. So for the rows, you're grabbing your H1, H2, and then you're grabbing the longitude, latitude, and price. Doing the same thing with H2, longitude 2, latitude, price 2, or you could define it by cols, which is the longitude, latitude, price, and you're just going through H1 to HN, H1 to HN, H1 to HN, depending on how you're doing.
And what's the equivalent over in the image data?
And the equivalent over in the image data is the actual pixels themselves. So depending on how you want to take the pixel, you can literally take an image that is pixels going across and rows and cols, and you can just set them up as a single matrix that's going all the way across.
Exactly.
And so you can just unravel it as a single. Would it be like, I don't know why, but I kind of want to say singleton, but that's not it. But you can unwrap it that way, and then you just do pixel 1, pixel 2, pixel 3, pixel 4, and then depending on the actual pixelation of it, 2 by 2, it would just be 2 to the second power or something like that, all the way down. Is there any? So what's weird about this, right, is because we're doing it by powers of 2 on image data.
What do you mean by powers of 2?
So currently right now, we're just doing 2 by 2, right? And then you can just scale up, and you can go
64 by 64, and then you unravel it into a giant.
All the way up to 4,
it's huge.
0, was 40, 90.
And
we'll like all the way up, you know? So what happens? The interesting thing here is what potentially happens when you're no longer doing powers of 2 on images, because some images, right, have some weird fucking dynamics where they have potentially a 256, and then it's times by like 1,825.
Draw it a 2. Let's Make a 2x3 image. Make two 2x3 images here, the way that I did it.
Okay. So we'll just do 1, 2, boom. So 2. I'll just do P1, P2, P3, and then I'll do the same thing right here. Doot.
We haven't unraveled them into pixels yet.
Yeah,
These are just images.
I'm just dictating 1, 2, P1, P2. I won't use P.
Yeah, don't use P yet. Yeah.
I'll just use like row.
Yeah. I mean, these are both just images right now.
R1.
You haven't unraveled them yet.
R2.
Yeah.
R3.
Those are columns.
Oh, yeah, you're right. Sorry. Colon, C1, C2, C3.
Yeah.
There we go. And we'll do the same thing here.
Yeah.
C1, C2, C3, then 1, 2.
Yeah.
And
now vectorize them and
Yeah.
organize them the way we did before.
And so it would be the same concept where I'll just put them down here. So it would be P1, P2, I see. So it doesn't matter.
Doesn't matter. Yeah.
I got you.
Yeah.
So it would
P4,
literally
P5, P6.
just, yeah. It would continue to go, and it doesn't matter.
Exactly.
One way or another.
Yeah.
Interesting.
Mm-hmm.
Okay.
As long as all of your images are the same dimension.
Yeah.
So usually when you have a set of image data, it's important that all of the images be the same dimension,
Interesting.
or else they won't stack into a matrix like
Right.
this.
So I see.
So they all have to be 256 by
yeah. So you
512.
do subcategories of dimensionality that are all the images, and you just say, okay, these images are this, these images are this, so on and so forth. I see.
Okay, so now that you understand the relationship between how you can just literally view all these types of data and you can organize it all the exact same way, just a matrix where the rows are your observations and your columns are your features. Right? Here the features are pixels. Here the features are, I don't know, information about houses. Here the features are a math thing that like just turns out to be a way to organize, to embed text into vectors. So now let me show you some cool shit.
Yeah.
Because we're going to start connecting this into geometry. So let's take H1. And let's say that the longitude is, I don't know longitudes and latitudes, so I'm going to make up 54 and 109. I don't know. And the price of this house is like, I don't know, 550.
By the way, I'm gonna spot check you at the end of this. If that's not a house for 550,000, this whole lesson is bullshit.
Oh yeah. So what we're gonna do here, we're gonna create a 3D. We're gonna create 3D.
I see.
So here's our x-axis, here's our y-axis, here's our z-axis.
Yep.
Let's say z goes from negative 500,000 to 500,000.
Okay.
Actually, let's go to
And then y
negative,
next will be log
let's
and
go to
lat.
negative 1 mil to a mil. Yeah, let's say x is 100 to negative 100, and then y is same thing, negative 100 to 100. So let's say that so our axes are like very differently scaled, just so that we can like look at it, right? So the z-axis is like scaled super like this, right? Anyway.
Yeah.
Now we take this observation and we're like, okay, 54 is like about here. And then in the y direction, we're at like 109, which is like here.
Yeah.
And then in the price, we're at 550,000, which is like here. So think of this as a point in 3D. So this is H1.
So
and it's a point in 3 dimensions now.
define for me. I see. Yeah. I got you.
Right?
Yeah.
So, and actually, let's just make this a little easier. And just because we only have a whiteboard and we can't like 3D model this shit, let's just make it 2D, right?
If only if we-
x-axis and y-axis. Right. So 100.
I was thinking if I blunder on my
100.
thing, I do not.
So this would be like this point.
I mean, it would have been fine keeping it as 3D. Like
Yeah,
my
yeah.
brain.
Yeah, actually, your brain works in 3D.
My brain
Makes
is
sense.
3D.
Yeah, it's just easier to draw it out.
Yeah, that's fair.
like this. And then let's okay, so this is a point in 2 dimensions now.
Yeah.
And
Dude, I've been
Okay.
working in 3D for 16 years.
yeah, actually,
That's a weird thought.
that makes sense. So this is the point 54 here, and then right here. Right here, this is what is it? What is it here?
That's 54, 109.
So that's the location of this
Yeah.
point. And you know, you can sprinkle in as many observations as you want into here, right?
Mhm.
So let's do H2. And what was it again? I don't remember. Let's do like 69 and
Good question.
42.
69. I like that you also asked what was it again. You never drew it to
I
begin
never,
with.
yeah. So H2 is I don't know, like here.
And then 42 is
here.
like right there.
Yeah. So here's H2. Now, with images, it gets a little harder to visualize. But remember how we had that 2x2 image,
Mm-hmm.
right? So let's
Yeah.
just, you know,
Bring it back.
1, 0, 0, 1. The second
Right.
image, you remember?
Mm-hmm.
So if we organize this
Yeah.
into 2D, right?
Black, white, white, black.
Yeah, exactly. So now, I don't know, I can't draw it, but imagine we like there is such a thing as 4-dimensional space insofar as we can't visualize it, but we know the mathematical properties of it,
Okay.
right? So imagine, okay, actually let's do it like this. So this is just barely in the point where there's like a way of thinking about it.
So 3D.
So here's 1. Here's 1. Actually, let's see, 1 is over here. So here we're at 1,
Mm-hmm.
0,
Okay.
0, and then time step 1. Okay.
What do you mean by time step?
I mean, we need to call something this 4th axis. So we're just going to say that time is the
I
axis.
see.
But just
So
as a way to
X,
think
Y,
about
Z
it or
time.
visualize it,
Gotcha.
X, Y, Z in time, right?
Yeah.
So think of like a 3D space that is evolving over time,
Mm-hmm.
and so you're at a particular time step of that space,
Yeah.
and then it's a particular point,
Yeah,
right?
it's a timestamp.
Yeah. So that's one way you can think about it. That's sort of a completely arbitrary way of thinking about it,
Right.
honestly, right? It doesn't really matter. The point is that there's a concept, and that concept is there's 4-dimensional space.
It's a way to ground the visualization.
Yeah,
I see.
yeah. But the point is that this object is a single point in 4 dimensions, just like each of these objects are single points in 2 dimensions.
I see.
So you can take that and roll with it, and you can just make big images, right? 250, 64 by 64 images.
Yeah.
You can unwrap them into
And then just
4096.
fit that into a single
And-
point within space.
And you can say that 4096 length vector is a single point in
So
4096 dimensions.
So here's a question for you. So the current photos that are being sent back
Mhm.
from the James Webb,
Yeah,
is
fucking
that
huge.
so that's a single point. Even
Yeah.
that alone, is a
Anything,
single
yeah,
point.
anything. It's a single point in ridiculously high dimensional space.
Yeah, that'd be crazy.
Yeah,
That's so much data.
yeah,
Those fuckers are massive.
yeah, yeah, yeah. So I mean, it would be an absurdly high space.
Right.
But the point is it's still
It's still a point
just a
in-
point,
within
and
how
however
much
many
space.
dimensions you're in, it's still just a point in space. And,
Oh, I see.
right, because you
so-
can always just unwrap it the same way
Yeah.
you did with the
So
small.
is the
dimensions.
dimensionality defined by the amount that you unwrap?
Exactly.
So it's like 0, 1 to n,
Mhm,
and so like this n
mhm.
being the dimensionality.
Exactly.
Oh, that's interesting.
Exactly. Yeah. So
Huh.
here, how many dimensions are there?
So that's so fucking cool. So before we jump on
yeah,
that,
yeah.
so in this aspect, if you unravel data like this within images,
Mm-hmm.
they log themselves.
What do you mean they log?
So, say we have a matrix of all of this,
Yeah.
and they all live within a certain dimension set.
Mm-hmm.
If all, say I have 100 images that are defined by where n is, and that's my dimensionality of them.
Yep.
All of those images are already on that dimensional plane. They log themselves. Like, I already know that there's 100 images on that dimensional plane.
Yeah, exactly. Yeah.
It's fucking genius.
Yeah. So that's 100 points in however many, right? If there's 64 by 64, that's 100 points, and those points live in how many dimensions? If each image is 64 by 64.
That's 64 dimensions.
No.
Well, wait, did you say
Each one is 64 by 64 image.
Oh, then it's going to be 64 to the 64th power.
No.
No? What would it be?
64 to the 64th power is 64
Massive.
times 64 times 64
Yeah, yeah.
times 64 times
So
64.
it's going to be
64 times.
64 times 64.
Exactly.
I see. Yeah, you're right.
Yeah.
Like 64 power.
So let's do a brief aside that's going to hint at our later discussion about basic functions.
Okay.
Turn this into 2 to the something power.
2 to the something power?
Yeah. What is 2 to the what equals 64? This is like a total aside.
Yeah.
But
2 to the 6.
so write it out like that.
So 2 times 2 times 2 times 2 times 2 times
And then, sorry, write out 2 to the 6th times 2 to the 6th.
Oh.
This is good though that you did this because it'll make what I'm about to say
Yeah,
easier.
let me actually move this down under it, because that way.
Cool. And then, what is the actual value of 64 by 64? Do you know that off the top of your head?
No. 2,000 something, 248.
Let's do. Let's make it a little easier. And let's say we have 16 by 16 images,
Okay.
and then this is equal to 2 to the 4th times 2 to the 4th. Which is, write it out the way that you just did.
I think that's
Yeah.
8.
Yeah. Put parentheses around them just to know where the 2 to the 4ths are, where each of the 16ths are. Cool. So, like, the parentheses don't matter. You can move the parentheses anywhere you want.
Yeah.
So how many 2's are there total?
There are 8.
Okay. So, so that means that 16 times 16 is the same as 2 to the 4th times 2 to the 4th is the same as 2 times 2 times 2 times 2 times 2 times 2 times 2
Right.
is the same as what? 2 to the what?
2 to the 8th.
Exactly. Sorry, 2 to the 8th underneath it. Okay, how does 2 to the 8th relate to this?
It's the total of the pixels.
How does the 8 relate to, like, how could you calculate 8 from just looking here?
Oh, it's just by themselves. It makes sense. Like, you would just add the 4's together.
Exactly, you would add them together. So that actually gets to something a little bit deeper, which is that there's this relationship where, so write this in terms of a logarithm.
Oh God.
Yeah. We're doing a brief divergence, but you understanding logarithms is going to be important later for loss functions.
I do not remember how. Would it just be log something? I don't remember how to write this. I'm gonna let you know that right now. That's why I need to do some base for it.
Yeah, think about it. Log base what?
That'd be log base. I'm not sure. I would throw out probably 4, but I'm not exactly sure why I'd say it. Yeah, I'm not sure.
So a way that you can kind of remember it is that the base is that when you look at what a logarithm is equal to, it's this thing.
Okay.
So log base something is equal to 4.
I see.
Log base something of something is equal to 4.
Log. Oh.
So like just looking at this, these 4s are the logarithms of this.
So
It's like a way
would
to
it
think
be
about it.
would it be log 2
Of what?
of log 2 of fuck. I can't remember how logs work.
See, this is what I'm saying is like
Yeah.
going back to the basics is like
Yeah.
having that shit intuitive is just like
This is actually
necessary.
a wonderful way of actually explaining this
yeah.
because it breaks it down to things that like I'm already familiar with.
Yeah.
So it's really good. Fuck, I can't remember how logs work. So can you explain to me? Explain to me, don't tell me the answer.
Yeah.
Explain to me logs in general.
The logarithm of something is the way to think about it intuitively is that the logarithm goes from the base space of the number, like it goes from the number itself
Yeah.
to the space of what the number is taken to the exponent to. So
I
like
see.
so for instance, when you're plotting something and
Yeah.
you say you turn it into a log axis on the plot. If you have a plot that looks like this, and this is exponential, and you move it into logarithm space, this is like 1, 2, 3, and so on,
Yeah.
4, whatever. You take the log function, right? That moves it into, that makes it look like this, where this becomes linear, and then this is 1 to the 1. Sorry. This is 10 to the 1, 10 squared, 10 cubed equals, 10, 100, 1,000, right, and so on, right? So going into log space means that instead of viewing things as the number themselves, you're viewing the like basic units as being how much 10 is going to the power 2, right? So the thing that's going up by 1 is the exponent of 10, 1,
Right,
2, 3,
3.
right? But
I
the
see.
actual number is going up multiplicatively, right? It's
Yeah.
getting multiplied by 10 every time.
I see.
So that's what a log space is. So that should be.
So is it always within 10?
That depends on the base.
I see.
Most of the
So-
time you're using base E, not base 10. But this is base 10. This
Yeah,
is
yeah.
log space in base 10.
I see.
But most of the time when you see log in practice, it's usually
What
base
is
E because
E? Euler?
Euler's number.
Euler's.
2.71828.
Euler. Yeah. I see. Okay. And so we want to do log of 2 to the 4th?
Log of 2. So the 4 is what the log is. 4
Right.
is the log.
4 is the log.
What's the log is
so
equal
it
to.
equals 4.
Exactly.
I see.
So now log 2 to the what? Log 2 of what equals 4?
Log 2 of 2.
Nope.
No? Would it not indicate?
So
Yeah.
if you take this expression, you're just reorganizing.
Yeah.
You're reorganizing this expression, but you're saying the same. It's the same pattern, but you're just reorganizing this expression into a different pattern.
Okay, say this one more time. So if I take this expression, so fx, so this is our
Is equal to-
expression,
Yeah.
is equal to this. And then we're defining the log 4,
Log 2 of what? is equal
log
to 4?
2 of 16.
Exactly.
I see.
Exactly.
Okay. That makes sense.
Yeah. So so usually you'll see like in practice, you'll just see like I don't know, log 100, right? Like this is how you would see it written out, and it's kind of annoying because they never use the base, but this just means equals, I don't know. Let's just call this log 10. So this is going to be 2.
Yeah.
Right?
Yep.
So, and let's say just log. So now let's define log to be ln, which is log base e.
Okay.
What's log base e of?
Why is ln defined as base e?
Log is usually defined as being base e rather than base. It's usually either base e or base 10, whether you're an engineer or a mathematician. Base e because e just has like beautiful mathematical properties. Basically.
I see. So it just falls into place.
It's just everything falls into place when you use base e, usually with logarithms. So that's why people often use base e. But like log of 1,000. Is this number going to be big or small?
It's going to be small.
Around what order of number?
I mean, it's going to be 10. If we're doing it base 10.
Nope.
Are we doing it base?
If this is base 10? What is this value equal to?
Would that not be 3?
It is 3.
Yeah.
Exactly.
Oh, what did I say? 10?
Yeah, you said 10.
Oh, oops. Yeah, I meant 3.
Yeah. So log of 1,000 is 3, right? Log of 10, what would that be equal to?
That'd be 1.
Exactly.
I see.
What's log of 1?
0.1.
Nope.
Log of 1 to base 10. Oh, 1 over 10?
Nope. Yeah, write it out.
Would it just be oh shoot, what would it be? It would still be, yeah. Well,
Fill in log of 100. That might help.
fill in a log of 100?
Yeah, in between those two things.
Okay. Equal to? Oh, 0.
Yeah.
I see.
And write this out in normal space instead of logarithmic space. Write out that log of 1 is equal to 0. So reverse the operation that you just did. Instead of going from normal space to log space, go from log space to normal space.
1 to the power of 1?
Nope.
Or 1 to the power of 0?
Nope.
Would it not be?
I mean, that is equal to 1, but that's not what the
Oh, not with the log is dictating.
that's not how you would write it out if you went back to normal space.
Really?
Write out this. Write out one of these down here in normal space.
Would it be then 1 times 1? Or would it be...
Write out log 10 of 100 is equal to 2. Write out this in normal space.
Okay. It would be 10 to the power of 2. This would be 10 to the power of 3. This would be 10 to the... Okay. 1 and 10 to the power of 0.
Equals 1. Write the equals too.
That would be 10. No?
Correct.
Nice. 100, and then 1,000.
Yeah.
Okay.
Right, so there's this relationship where depending on what base your logarithm is, every time you add 1 to the logarithm function, you multiply by that base over here. So let's move to ln. So ln of
Euler 2.
So do write out what these would be. Log base c of e squared.
Do you want me to actually put Euler's number?
Put in what the result is equal to of log base e of e squared.
I guess it would be 2e, or I don't think that's right.
Yeah.
Can you tell me? So is Euler's number? So here's a question for you. Euler's number. Is it always represented as e, or is it represented ever in its number form?
You could represent its number form if you wanted, but you wouldn't be precise because it's an infinite.
It's an infinite set.
It goes on forever. So
yeah, I shouldn't
so
say
you just
set,
say e.
but
Yeah.
okay, so e is how it's represented within that.
Yeah, just like pi is in.
Yeah, which is infinite, goes on forever.
But that's around equal to 2.718.
Yeah. E to the power of 2 log.
One thing that might help is look at the example with tens and view the things in the parentheses differently. That's my hit. And then use the pattern to figure out the E one.
Let's just do log.
Yeah, exactly.
Which would equal 2.
Yeah,
So then it would be, would it be 2, 4?
correct. Yeah, exactly. Yeah, that's exactly correct. Nice.
Okay.
So think about this, right? E squared is kind of a big number. E to the fourth is a really big number.
Right.
Every time you multiply by e, you add 1 to the logarithm function.
Yeah.
So, like if the output of a logarithm function is like 100, that means that you took something to the 100th power, right?
Yeah.
So logarithm space is like you're basically compressing bigger and bigger numbers into being like additions instead of multiplications.
I see. So you're
right?
you're making a very unruly number.
Yeah.
You're able to actually start working with it.
Yeah, you're like basically compressing all of space so that you can see really big numbers as just like small like.
See, if they taught math
Linearly
like
smaller numbers.
this is fascinating.
Yeah.
Like if they taught math like this, instead of just being like, hey man, we gotta learn some stuff.
Yeah, yeah.
And let's not explain why it works.
Dude, I don't know why people don't teach math the way it should be taught, which is, I think, like this.
Yeah.
Where
This
like
makes
you're just
perfect
thinking
sense.
about things scaling and like thinking about it like
Well,
this.
it makes perfect sense.
Much
Not
better.
only that, you're able to actually understand the relation.
Yeah.
Whereas, like, if you don't teach that and you just teach the functionality,
Yeah.
you don't hone in on the relation
Yeah.
of how things ideally would work.
Yeah.
Because when you're working with log, it's just solely data across the board,
Yeah.
and then it falls into place.
So now next thing, what is log of 0.1? We're in base 10 again.
Base 10 again.
Yeah, this is base 10. Log
Yeah,
base
yeah.
10 at 0.1.
Okay. So, quick question. So if it is Euler's, so I'm gonna move this because I just want to put it up here. You okay with that?
Yeah, that's fine.
But this is more for like recognition, right? This is more on the line of dictating by by right, like not by like right as in RIGHT, but W. All right. So when we put ln, that will always be log of Euler.
Yeah, log base E.
Log base E. So this ln, I just want to make sure that I get this down. Ln is always log base E.
And a lot of the time, so Europeans use ln all the time.
Yeah.
A lot of the time in America, people just say log and they mean base E. It's sort of annoying because I feel like
Really?
log
Yeah,
should
yeah.
be base 10, but a lot of the time people will just say log. Like in NumPy, if you say log, it's base E.
Really?
Yeah. np.log uses base
Within
E.
Python. That's kind of annoying.
Yeah. Well,
I mean,
it's not annoying to a
for-
mathematician
yeah.
because a mathematician almost never uses log 10.
Right.
Because log 10 just like doesn't like, it's sort of random, right? Log 10 doesn't really have interesting properties, but log E has a lot of interesting properties that mathematicians like abuse all the time.
Yeah.
So that's why everyone does log E, is because it just has
I see.
good mathematical properties.
So we were doing log base 10. So
And log base 10
that-
is how you can think of it to get an intuition for logarithms. In practice, it's usually going to be base E,
Yeah.
but log 10 is like, we kind of think in tens. So
Yeah.
it's just easy to use log 10 to think about how
I mean,
logarithms work.
it's easy to like make them larger
Yeah.
very, very quickly.
Yeah.
Whereas if you're using Euler's number, it's an infinite space. So it's hard. Hard to picture.
Oh, I see what you mean. Like it's
Yeah.
not like you can't calculate it.
Yeah,
easily. Like
exactly.
E squared is kind of hard to calculate.
Yeah, exactly.
Yeah.
It's something that is so astronomical
Yeah.
that it's
Well, it's not that it's big, right? E is 2.182.
right. But
so E squared is just
it goes
around 2 times
infinitely.
2.
So it's
Yeah,
not,
yeah, the
it's
number
not,
goes
it's not
infinitely,
that
yeah.
it's big
Yeah.
in scale.
Yeah. Oh, I see what you
It's
mean.
big
Yeah.
when it goes to
Right.
the actual space of
Yeah.
which the number takes up.
I see what you
And
mean.
the
Yeah, there's a lot
calculation
of
of that-
decimal points.
The calculation of that is, you need a fucking supercomputer.
Well,
So, like-
you would. There's no like if you
Yeah.
wanted to get the full calculation,
Right.
you couldn't.
It's impossible.
Yeah. Yeah.
And
It's an
that's the
infinite
thing, right?
numbers.
So, where this, it's very easy to kind of grasp because you're like, it's something that I use daily.
Anyway, so let's get back to this. So I just want to do
Let's
what's log base 10 of 0.1.
0.1 or
Point 1. 0.01 is fine too, though. You can do that if you wanted.
let's do 0.01. Why not?
Cool.
Okay. Let's see what we got. Would it just, and it's log base 10,
Mm-hmm.
would it not just revert back to 0?
Nope.
Interesting. So this reverts to 0 because it's whole.
Let's-
It goes into it.
Here,
Makes sense.
let's take a break real quick and do a quick divergence.
Okay.
What is 10 to the negative 1?
10 to the negative 1.
Mm-hmm.
This is where you're gonna find really weak math in my brain.
Yeah. See, that's why we're doing this, man. We're going back, because if you don't understand this, you will never understand
Yeah,
other
yeah.
stuff.
No, this is brilliant.
Yeah.
I love this.
Yeah.
10 minus 1, what would that be? 0? No. Yeah, I'm not exactly sure how values play off of negative powers.
Yeah, well, so let's think about the pattern. So this is a great instance of thinking about patterns. So what happens when you go?
Oh, is
What
it
happens when
literally?
you go this direction?
I see. So would it then just be like negative 1 is 10? Would it then just dictate negative 10?
Nope.
No.
No. What happens when you add 1 to the exponent here? What happens when you go from here to here?
You 10 times 10. So you just would do 10 times 10, which would go to 100.
Yep. And
Yeah.
then what happens when you go here?
It would be 100 times 10.
And then what happens when you go back down here?
It would be 1,000 divided by 10.
And what happens when you go here?
100 divided by 10.
And what happens when you go here? This is wrong. Change this to 1.
Yeah, sorry.
what happens when you go from here to here?
It would be 10 divided by 10.
So what happens when you go from here to here?
1 divided by 10.
Exactly.
Interesting. Okay. So it would be, I see. So this right here, 10 to the negative 1, would be would it be 0.01 or would it just be 0.1?
0.1.
Yeah.
Because 1 over 10.
And
Now
then,
do 10 to the negative 2.
so 10 to the negative 2 would then be, negative 2 would then be 0.01.
Exactly. So to
I
go
see.
one less in logarithm space, you divide by the base one time.
I see.
And to go one more in logarithm space, you multiply by the base one time, right? So if you're in base E, right, you would divide by E or multiply by E to go one forward or one less in logarithm space.
That makes sense. We divide.
Mm-hmm.
By base. I'm just writing this down so it kind of
Yeah, perfect.
uh,
Yeah, going one back in logarithm space.
going forward
Yeah.
in log space.
Mm-hmm.
We multiply by the base.
Yeah. All right, I have to go to the bathroom, so I'll be right back. While I'm gone, here's what I want you to do. You can pick your own adventure. You can either look at this stuff and think really hard, and you can try to visualize the logarithm function and try to visualize like different bases and like how this all translates to different bases and just think about how the function works, right?
Yeah.
And try to get it intuitive. Or more specifically, if you want, you can do everything that we just did, but with base E instead. Or just think of some way to think about this deeply.
So what I want to do, in all honesty, is I want to think about it deeply, and then I want to tie it back into our graph.
Okay, cool.
But then I want to revisit it after.
Yeah. All right, that sounds good. I'll be right back. Wait, which graph? This one?
This one. This one,
Oh,
because
that
we're
one?
defining
Yeah.
within space here.
Okay, cool. Yeah.
Make sense?
Got it.
Okay. Alright, so I'm going to talk about this out loud. So, unfortunately, whoever might watch this in the future, you're going to hear potential madness or something that is complete bullshit. But we know for a fact that within logarithm space, we're either going to be multiplying by the base, so dependent on if the base is base 10 or Euler's number, no matter what that value set is, it's going to be multiplied by that base. So for example, log 1 is going to equal 0, which would then be, I see. Yes. So log 1 would be 0, but that would be defined as 10 to the 0, which would be 1. Then log 10 equals 1, which would be 10 to the 1 power, which would be 10. So 10 times 1. Then you'd have log 100. That's 2, so that'd be 10 times 10. And then you just keep multiplying, and then you'd be going back in space by dividing. Okay. Yes.
Cool. So, in general, the intuition is that logarithms are a function that takes really small numbers, and every time you divide by 10, when you're in the space of 0 to 1, you can get really, really, really small. and it just turns it into like a not so small negative number instead. Because
Right.
you divide by 10 4 times, that in logarithm space with base 10 it becomes negative 4. And you multiply by 10 4 times, in base space, right, that's 1,000,
Mm-hmm.
and in log space that's just 4.
Yes.
So logarithms, so now what I want you to do is I want you to draw what the logarithm function looks like.
Oh, interesting. Yeah.
And we'll just use log 10.
Okay.
So 1, 2, 3. Let's do this. 1.
Actually, I think I'll keep it here because I'm gonna use my left hand to draw.
So on the x-axis is the number, and on the y-axis is the number passed through the log function.
I see. Yes. Okay. Do you want?
Start with the and then actually I'm gonna add that too. Oh, and then I'm gonna do
It's -1 on that side.
oh, that's 0.1.
Oh, that's 0.1. Okay, I see.
0.1, -5, -2. Okay.
I was very confused for a second.
Yeah.
I was like, Alex.
Yeah, it's 0.1.
Okay. So which function here would you like me to draw?
Log base 10.
Log base 10?
Mm-hmm. Yeah. And then you can think about how everything turns into log base e. Because it's a direct translation. It's just your log base e just means that you're scaling a little bit slower.
Mm-hmm.
Because it takes a lot more times of e multiplying itself by itself to get to 1,000 than it takes for 10 to multiply by itself. Like 10 only has to multiply by itself like 3 times to get to 1,000.
Yeah.
And e has to multiply by itself like, I don't know, like 9 times to get to 1,000.
Yeah.
So in log space, everything's stretched out a little bit more. Like
So-
instead of 3, it'll be like 9-ish.
Right. So the graph is currently within log space.
Yeah. Well, this is you're graphing a function where you take the input here, and then up here you're saying what does that input become?
Right.
So if you take 5, what does log of 5 become? And then if you take 10, what does log of 10 become?
I
And
see.
so on.
I see. And we're doing it by base 10.
Mm-hmm.
Correct.
Base 10. Yeah, exactly.
Oh. We're just gonna do this real quick.
Mm-hmm.
Log base 10.
That'll be a bit harder. You'll need a calculator for that. Because what does that mean?
Well, that would be base 10 of 5, which would be defined by. Oh God. Yeah. It would be divided by, would it not? It's over. Well, I guess that's going forward. Multiplied by the base. Would it not be?
No.
I see. So it would be something along these lines.
Mm-hmm.
It would be.
This
like
one is not
2
going to be.
It would be like 2 point.
It'd actually be like, well, what would 2 point something be? What is
Would it?
what's log
Would it be yours
log
number?
10 of what is log 10 of when the equal sign is 2? Like when log 10 of something is equal to 2, what's the something?
100.
Yeah. So would log 10 of 5 be greater than or less than 2?
Oh, it would be significantly less than 2.
Mm-hmm. Yeah.
I see.
Because log 10 of 10 is 1, and log 10 of
So it would be
100
like-
is 2.
It'd be like point, who knows, 0, 1, blah, 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 blah.
Nope, not that either.
No? Would it
Because
not?
what's log 10 of 1?
Log 10 of 1 is... zero.
Mm-hmm. So, actually, yeah. No, actually, you're right. Yeah, it would
Yeah.
be. Sorry, I just had a brain fart. It would be like 0 point something.
Yeah.
Yeah. So.
I was very
Sorry.
confused.
No, you're right. It's 0 point something. It'd be like
I
0
don't know-
point like.
I don't know what it is.
Exactly. Like you'd
But
need a calculator.
It
So
would,
like.
it would go all the way to like somewhere over here.
Yeah. So like just looking at a calculator, it would be log 10. Whoops. 5. The log 10 of 5 is like, it's like
Yeah.
0.698.
But that's so interesting because that just means then that this gets stretched. Like
Exactly.
it doesn't even go up. It just like
Yeah.
it stays so close to
Yeah.
this value set
Yeah.
that it just does that
Yeah. Nice.
continuously throughout.
Nice. Exactly.
And
And it
then,
goes
like,
a little bit up,
A
but
little bit up.
but it goes
would-
even less up the more far you're
It would
going.
need an astronomically large number to get anywhere.
Yeah. Exactly. That's a fundamental property of logarithms. But now.
That's fascinating.
Now let's go back from 1. Let's go to 0.1 and 0.01. Let's get closer and closer to 0 and look at what happens. Because there's a part of this function that you haven't drawn.
That's so interesting. So if we get closer to 0,
Yeah.
is it not going to shoot up? Hold on. Let me think.
Yeah.
Oh, it's going negative.
Mm-hmm.
Interesting. So it would go on the negative axis now.
Mm-hmm.
And the question becomes, oh. I'm trying to think if this here
Mm-hmm.
would be on. Hold on. Let me readjust.
Yeah.
So it would be on there. Okay. That is fascinating. Hold on. I'm trying to think about this.
Yeah.
So I'm going to draw this real quick.
Mm-hmm.
So say we have getting closer to the negative. You said what? Negative?
We're getting closer to 0.
Closer to 0.
Mhm.
Okay. So I just want to do negative base 10. Let's do like 0.01.
Mm-hmm.
We'll do kind of what we did up here, where we defined this, and then that came out to be, so that's base 10, so that'd be like power of 2.
Yeah. Think about this. How many times are you dividing 10 by to get to this number?
Yeah. So it would be 10 to the negative 2 power, so it would be divided by 10. So twice.
Yeah.
So
So what would that be equal to? Log 10 of 0.0. Yeah, exactly. 10 to the negative 2. Yeah. Because you start at 10, you divide twice, you start at 1, you divide twice, and you get to 0.01. You
So
divide by
my-
10 twice.
So my question is, it it's either shooting off this way because we're using this 10 to go to the negative that way, or like I don't see any way for it not to potentially shoot off this way in some manner.
Yeah.
Because it's gonna just go
Exactly.
like down that way, because it's not gonna do some form of symmetry here. It will literally do, as we get closer and closer.
Yeah, you keep dividing by 10 and dividing by 10 and you get 0.01,
It would just go like all the way down this line.
Exactly.
So it would go infinitely down.
Yep. So, so this is what the logarithm function looks like. So you fucking nailed it.
Yeah, suck it.
Nice job. So, so now I have another question.
Yeah.
Should you think of this as shooting down super fast? Or should you think of this thing, because it looks like it's shooting down super fast right now. But think about this line. Think about how fast this thing is shooting down.
Oh, it's not shooting down fast at all.
Exactly.
It's literally crawling.
It's crawling, and that's like a thing that people like often misinterpret about logarithms, is they see this and they're like, oh, this is going down super fast.
I think what
no,
it
it's not.
is they see the extreme
Yeah.
turn to it, and then they go, boom.
They go,
up here, it's really quick.
Yeah.
It's an instantaneous turn.
Yeah.
But once you get down here, it's crawling to get to 0.
Yeah, yeah. Because, like, think about this. You divide by 10 100 times. That's such a small number, right?
Yeah.
That's like 0.0000000000000 whatever. Like, so small of a number.
Yeah.
And that's only negative 100 when you take the logarithm of it. Like, right? Like, that's not that small, right? So when by the time you're here, you've divided by 10 times. That's 0.00000000001.
Yeah.
Right? To get to here. So this thing that looks like it's going down super fast is actually going down super slow. It's just that if you like zoomed into this area, you'd be able to see that.
Yeah.
Yeah, because it's
This
yeah.
right here is Fast and the Furious, baby.
Yeah.
That's family.
Yeah, yeah.
This down here is slow.
Yeah.
This down here is the sloth DMV of Zootopia.
It only looks fast because you're not zooming in as you approach
Yeah.
0. Anyway, so that's logarithms. So that was a brief divergence, but I think I wanted to, and I think so. So just to give you some context here, so I did basically what you're doing right now, like near the end of undergrad. So what I did, I was like, oh shit, I don't know math. Because I had just taken a bunch of neuroscience and biology classes.
Yeah.
So at the end of undergrad, like I did exactly what you're doing right now. Like I went back to these basic functions. I like went through Khan Academy. I like went up to whiteboards and like thought about them really deeply myself. And that's how I got to understanding it the way I do now.
Yeah.
Is like basically doing what we just did, but by myself, and doing it like a bunch more times. So I think the total number of times that I did with logarithms was like 4 or 5 times, just like drawing stuff up on the whiteboard and like thinking, like closing my eyes and thinking really hard about like what you just did, about like how the function works and like what it is intuitively and like what it actually means to take a logarithm of something. And then I like looked up the properties of it, but then I didn't just like memorize them, but I thought about what they meant in terms of like this knowledge, right? Like I thought about how those properties related to like the intuition that I had been building up.
Yeah.
And I think if you do this, like maybe go back to logarithms like 3 or 4 more times and just do this in front of a whiteboard and like think about like different, like, right? Don't just do the same thing over and over, but like different ways of viewing it, do different things, right? Understand them in different ways. And I think if you do it like 3 or 4 times, you'll have a great intuition. And then if you do that with every basic function, sine and cosine, exponents, polynomials, even like multiplication and division, right? Like actually, let's get a sense for. Let's go even more basic.
Yeah.
How would you think about?
I need to go back and reread that book.
Which book?
The book you recommended, The Basics of Math.
Yeah. That book, I read that book during the time period that I just told you about, where I was going back, and it was fucking amazing for that. So, okay, so how would you think about this one, this number? First of all, what is that number going to be? Is it going to be like small, big?
Yeah, it's going to be small.
This whole number?
Oh, that whole number?
Mm-hmm.
I was not
10 over
looking.
1/10.
10 over 1/10?
Mm-hmm.
Do I not know basic division?
It turns out that a lot of people don't.
I was like thinking I'm like I should know this. This should be almost instantaneous.
Yeah,
and I
everyone thinks
started thinking about it, and I'm like, wait a minute.
And bro, this is why everyone's fucking bad at math. Like everyone's like that. They're like, oh, I took lots of math, I must understand it. And then you ask them what's 10 divided by 1/10, and they don't know. You're not alone. Like this is what it is.
I have no shame.
Yeah.
So it doesn't bother me. I'm actually gonna post this recording on my company's thing and be like, yo guys, join my journey.
Yeah.
I have no shame.
Yeah.
Like I think that's the folly of most people.
Yeah.
They don't want to seem weak.
Exactly.
Or like not.
Dude, no, like when I was going back to this, I realized that I didn't fucking know what that was. And that's when I was like, that's why math doesn't make sense.
Yeah.
I don't fucking know what 10 over 1/10 is. Of course I'm not going to understand more complicated stuff. It's all built on top of that.
Yeah. I would assume it would go up. I would assume, like, even though I don't know, like I'm telling you right now, I don't know.
Mm-hmm.
But I would assume it would go up. I would
Yeah.
assume it would go to like 100 or something.
Yeah?
Yeah.
Yeah, it's 100. Why is it 100?
That's an excellent question.
Yeah.
let me write it out.
Yeah. Don't write it out the way that you would normally do it, where you like fucking do the algebra rules and fucking flip them and shit. That won't give you an intuition. That's what everyone does to learn it, and then they don't get an intuition, and that's why they don't fucking understand.
I don't even remember that.
That's fine. You don't need to. Don't think about it like that.
I'm not thinking about it like that. I'm just thinking about it in the sense that generalized, this would be 0.01.
Mm-hmm.
And then you would divide that by 100, which, or not 100, you divide that by 10.
Well, you don't divide that by 10, you divide 10 by that.
Oh, so we're dividing 10
10 divided by and that's not 0.01. 1/10.
Is it, oh, it's 1. 0.1.
0.1, yeah.
Yeah, sorry. Okay, so 0.1, yeah. I would assume, because it's that 10th and you're dividing it by a 10th.
You're dividing 10 by a 10th. Yeah.
That you would actually go up and add a 0 because...
Don't think about adding zeros. That doesn't you don't understand it. Yeah, that's not how you understand the intuition. Don't think about like adding or
dividing,
taking away a 0.
Anything.
Think about numbers and then like how they scale. Think about it intuitively. Think about like what is that operation doing to 10? And what is that operation telling you about the relationship between 10 and 1/10? Think about it like that.
Okay.
Don't do the bullshit where you flip the thing and then do it computationally. That's how you don't actually get an intuition for what fucking division is.
Give me a second.
Yeah.
I actually need to think about this.
Mm-hmm.
One day I'll be good at math.
Mm-hmm.
I'll learn math, Alex.
Yeah.
One day.
Yeah.
Today is that day. I'm not exactly sure what it's doing to it, because you have 10, right?
Mm-hmm.
And then you're trying to force 10 into a decimal.
No.
Yeah, I'm not sure. I'm not exactly
Think
sure
about
how to.
think about this. How many 1/10ths do you need to make up 10?
A lot.
How
You
many?
need 100.
Exactly. That's exactly how many 1/10ths you need to make 100 to make 10.
That's hilarious.
Yeah. Yeah, you need exactly 100 1/10ths. If you take 100 1/10ths and you smush them all together and you sum them, you'll
Yeah.
get 10 total.
Fucking wizard shit. This is why, I think if people learned math this way, right, and not in the way that's currently set up within universities.
Mm-hmm.
That's right. I work at a university. I'm saying this on video. Universities need to fix their shit.
Well, I think grade schools.
Yeah.
It's not universities that's causing this.
Well,
It's grade schools.
I think universities need to fix their shit
Yeah.
as well. But in general, yes, I agree.
So, so getting an intuition for this, I think, is also going to be important. So go back to shit like this and think about it in terms of
just base understanding.
think about the base understanding. Yeah. Think about here. This operation is literally saying, how many of these things do you need to sum up to make 10?
Right.
Once you're in continuous space and you use decimals, it's not really summing up anymore, but thinking about it discretely and thinking about summing up stuff is
Yeah,
good
it
for the
helps.
base intuition. And then you fill in the middle, right? Instead of right, you think about it continuously instead, and then that's how you'll build the intuition is you take you take here's a 1/10, here's another 1/10, here's another 1/10, right? You put them all in a bag.
Say bag again.
Bag. Here's another 1/10, right? You say how many 1/10ths do you need to put in this bag to make 10? You need to put 100 1/10ths in this bag to make a single 10.
Why do you say bag like you're from Canada?
Bag,
Bag.
bag, whatever.
You're from Seattle, dude.
Yeah.
I mean, granted.
So
you're
how
close
many
enough.
1/10ths is this?
4. So there's 4 1/10ths in that bag.
Yeah, which is what number?
Oh dear God, you dick. 4/10ths.
Exactly. 4/10ths. And then if I add a few more 1/10ths,
Oh.
let's make them all fifths.
Okay. You're like, I'm gonna have to add a lot of 1/10ths to this bag.
How many 1/5ths are there in here?
6. 6 over 5.
Yeah, 6/5. All right, and then if you have a single whole, right? How the fuck do I? 1, 2, 1, 2, 1, 2, 3, 4, 5. Right? You have here's one of the 1/5ths. Here's another one of the fifths. 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 And then you have one more 1/5. And so you have 6/5 total
I see.
when you put them all together like that.
Yeah.
And
Thinking it like pizza, baby.
yeah, exactly. So let's see. Another good one to do is the operator A times B.
Mm-hmm.
You have, say A is 10 and B is 3.
Yeah.
What is this operation actually doing?
This operation is multi.
There's 2 ways that you can think about this operation that I want you to realize. And don't say it's multiplying 10 times 3 because no shit.
There you go.
Yeah,
It's adding 10 of itself 3 times.
perfect. Now, what's the other way that you can think about it the same way? You sum things.
You're adding 3
Exactly.
by itself
Perfect.
10 times.
Yeah. Nice.
8, 9. There you go.
So the reason that I'm going over this is because this is actually going to pop into play later when we talk about matrix multiplication.
Interesting.
So this is actually a useful, because there's an analogy here to matrix multiplication. In this instance, you're saying that 3 is an operator, let's call it a function, is a function acting on 10. Right? So you take 10, and then you take the multiplied by 3 function, and then now you have 3 10s. Okay?
Yep.
Later on, when you stop thinking about it discretely and you think about it continuously, you'll think like 3 is a thing that scales 10 by 10 3 times, right?
Yeah.
2.5 is you're taking 2.5 10s, right? You scale by a factor of 2.5, right? Down here, 10 is a function
of 3 or on 3.
Yeah, acting on the number 3.
Yeah.
Acting on 3. So I'm going to take this idea where you can think about the operation of A times B as either B being a function acting on A or A being a function acting on B. Both of them are equivalent. It's just a different way of thinking about it.
Right.
And you can think about that. That's there's 5 ways of thinking about matrix multiplication that I want to teach you later. And 2 of those 5 ways are a direct analogy of this idea, where if you take the matrix A and B, one of them is you can think of B as being a set of vectors and A as a function acting on it. Or you can think of A as a set of vectors and B as a function acting on that. And it's the exact same idea as...
Say that one more time.
So say you have this is a sneak preview because I'm not going to get into this deeply now.
That's fine.
But if you have the matrix thing AB,
Yep.
where A is, let's get used to this notation. Let's say A is a
Is an element of
n by m matrix, and B is a m by p matrix.
Okay.
So first of all, let's just take a brief aside to talk about this notation. So what this notation means is that A is an element of the set of all matrices that are comprised of real numbers meaning any number, including like any number that's not a complex number, right?
Yep.
Any number that there's no imaginary component, right? So anything from negative infinity to infinity, right?
Yep.
A is a member of the set of all matrices comprised of real numbers that have n rows and n columns. So up here, this is a member so this matrix is a set of R of what?
R of R of n times n, but n being h and m being long to the lat.
What's the actual number? What is n as an integer?
2.
Yep. 2.
So it'd be 2 times 2.
Exactly. So this matrix is a member of the real numbers of the set of all 2 by 2 matrices.
Right.
So that's like kind of an important aside, right? Just
Okay.
notationally, that's what this notation means. This element thing means it's an element of the set. This is the thing that defines that set.
Yep.
And that set is all 2 by 2 matrices
Yeah.
where the numbers are real numbers.
Right.
Okay. So if you take A times B, A is think about it like this. There's n rows and m columns. B is B is a matrix where there's m rows and p columns.
Okay.
Okay. You can either think of this operation as this matrix is a function that acts on all of these rows to create a set of new rows, each of which were passed through this function.
Mm-hmm.
Or this operation is these columns being acted on, each one of them being acted on by this whole function.
I see.
And thinking about it in these two different ways is exactly analogous to thinking about this like this versus this.
It comes all the way back to what we did with the longitude and latitude, where we had the two different setups for making the rows or cols based off of H1, H2, and longitude, latitude with price. It's the exact same kind of setup of that, except this is more along the lines of actually how they would play with each other. Does that make sense?
Yeah, kind of. I mean, we're just kind of starting to get into this whole matrix operations idea, but I just wanted to cement the fact that there'll be a few other ways. I'll introduce a different way of thinking about matrix multiplication first, but two of the ways that I'm going to show you are literally direct analogies to this.
Yes.
And in fact, they're literal direct analogies, meaning if you view A as a 1-by-1 matrix and B as a 1-by-1 matrix, it's literally the same thing. It's not an analogy.
Really?
It's exactly the same thing.
Interesting.
Right?
So this is super important. Okay.
Yeah. So like here, this is literally A is a member of the set of all 1-by-1 matrices, and B is an element of the set of all 1-by-1 matrices.
I see.
So M is equal to 1, N is equal to 1. Sorry, N is equal to 1, M is equal to 1, M is equal to 1, and P is equal to 1. But this is literally the same thing as this. It's just that now it's 1-by-1 matrices, right? And you can think of a number as just a 1-by-1 matrix.
Huh. That's cool.
Yeah. So, okay. So this is all like kind of an aside. I just want you to start thinking about this for later when we start thinking about ways of understanding matrix multiplication. And I want you to think of logarithms sort of by themselves, because in parallel, we're gonna kind of try to understand all the basic functions and get like a real understanding of them instead of the, bullshit pretend understanding that you learn in high school or elementary school or whatever. So, okay, what do we want to do next?
I don't know.
So let's go back to.
I'm along for the ride, baby.
Let's go back to this whole concept. So we're gonna backtrack in time.
Okay.
We're gonna go back to when we were talking about these things.
That sounds
all
good.
of this was kind of a big, very important side quest that will come back later.
Side quests are my favorite. That's the only thing I did in Skyrim.
Yeah. So one piece of homework that I have for you.
Yeah.
If you want to do it.
Yeah, man. Like I said, this is literally what I'm gonna do tomorrow night.
Yeah.
Go back to elementary school, you loser. Man, Alex, that's mean.
Yeah. Okay. So go. Like, I'm not gonna tell you exactly which ones, because I just want you to do it independently and figure out what you need to know and what you secretly, you didn't realize that you don't understand 10 over a 10th. Like, no one does, but then everyone actually doesn't know what 10 over a 10th is, because no one actually understands it deeply. So what I want you to do is I want you to aggressively hunt through your basic math knowledge. Go to the internet, find properties of, basic algebraic properties, properties of manipulating numbers, right? Where it's X and Y, right? like all the properties of like, the distributed property, the multiplicative property, all the basic algebra properties that you learn in like early high school or whatever. I want you to go back to them, and I want you to have like a whiteboard or that thing, and I want you to start doing the same thing that we did with logarithms and 1/10, where you don't understand them by rote, but you go back to them and you start thinking about them
Right.
in terms of what they actually are.
Yeah.
Right? And you're gonna have to think harder than you did in high school in order to do that, because you're thinking about what they actually are now instead of learning the properties by rote. And why they and you'll know that you're making progress when you look back, and it's just like obvious to you that like, of course that's the property. Like there's no other way in which it could be that. It's just, that's what the pattern is. Like, it's not like you have memorized it. It's like, it feels to you like that's just the obvious way that the universe has to be, because you see why it is the way right? You see the way of viewing it that means that that's how it has to be, right? Okay, so that's the homework, is start doing that. This is going to take you longer than just one time doing it. Probably what'll happen is that
doing it a lot.
You're going to be, you're probably going to have to do it like a bunch of times, and you'll have to think about each one separately, and then it'll start going faster and faster because you'll start to like see connections between them, right? And like Khan Academy is great for that, I think. Well, it's great for like remembering what the fuck they even are. But even just like basic like kids math websites, right? Like I did that when I was doing this, right? When I was going back, like I literally went on to like kids math websites and like Khan Academy for fourth graders, fucking like re-understood it, but more deeply as an adult. And like I think that if more adults did that and set aside their pride and realize that like when you're a kid, your first priority is not thinking about something deeply, and you'll never understand it deeply until you go back to it. Like that's the secret to like understanding math really well, is understanding these basics way more deeply than anyone else does. So okay, so going back to vectors.
Okay.
So we're going back to vector land. Okay. So first, I guess I want you to reiterate all this stuff, right? So I want you to tell me like what we talked about before with this stuff, because now we're switching back into this whole.
So we literally are just mapping these value sets, these matrices, onto graphs. So we're defining, say,
not graphs. Think of it as in space.
In space.
Literally,
yes, points in space, dimensions.
Points in space. Yeah.
So, do we want to think of it
probably
as,
because you know 3D really well. Think of it as like literal points in 3D space. Think of like this place in front of you. Here's an x-axis. Here's a y-axis. Here's a z-axis, right? And so if you have the vector, say you have the house 54,109, and then like I don't know 500,000, like we did before, right? And let's say the z-axis, which is like this, up and down. Let's say the z-axis. Let's say the z-axis is like really stretched out, so that this is 500,000, even when this is like 100. Okay. So, right, if here's 0, here's the x-axis, here's the y-axis, here's the z-axis. Where would 54,109, 500,000 be? Starting from my finger here, which is 0.
So starting from here,
that's the 0.
what are we defining long and lat as?
X, Y.
Okay.
Yeah. Actually, I would actually say, let's call the axes, so this is a bit of a peculiarity, but let's call the axes x1, x2, and x3.
I see. So,
and the reason that I'm doing that is that Y often is defined as being either a label in machine learning for an observation, or it's defined as being the result of a function, like log of x.
I see.
Right, so like there's a fundamental difference between this graph and this graph. There's a fundamental difference.
Interesting.
I want you to tell me what that fundamental difference is between this graph that we made here and then this graph where we're plotting these. They're not at all the same thing, even though they look like the same thing.
Yeah.
So what's the fundamental difference between this and this?
Besides this one being potentially a three-dimensional graph, this being 2D.
Yeah, let's just say that this is 2D.
Okay. This graph is going infinitely.
No.
No?
No.
So, there goes that finite to infinite analogy that I wanted to do. The fundamental difference then would have to be the definition of the axes, you know?
Yep.
Because
You're onto something.
So the fundamental difference is you're actually dictating. We're not. That one's not. It's not thinking about it. That doesn't make sense in that scenario. But there is a difference within the axes.
Yep. Keep going down that line of thought. That's a good line of thought.
Is it the sense that the axes are defining dimensionality
In where are they defining dimensionality?
within space?
Where? What do you mean by defining dimensionality? Be more specific.
So when I mean defining dimensionality, I mean that they are defining. How should I put it? Do you have a? Give me this. So within this graph, they're defining dimensionality within space by defining. Come on, Daniel. Shit. Thought I had it. Give me a second.
Yep. Think more about what the axes mean.
Yeah. Well, we can define these as x, y.
Sure.
And to be fair, though, we can define these as x and y as well.
Yeah, but don't do that. That's the whole reason why I define that. Why I'm calling this x1 and
Right.
x2, and
Well,
this is x and log of x, is because I want to emphasize that this is fundamentally a different thing than this.
I see. So the axes are different within this because in here we are not. We're trying to find a singular point in space.
Good
And
line
so
of
we're
thought.
using defined axes
Mm-hmm.
within the dimensional space that we know
Yep.
to get that singular point.
Okay.
Whereas here
Yep.
we are doing. Here we don't care about a single point in space.
Yeah.
So we're just having a graph that's defining the log and the x, and then we're just grabbing a curve based off of it. So within that sense, we don't care about dimensionality here. That's not a thing.
Mm-hmm.
That's bullshit.
Yeah. Well, we kind of do, but
Do
the
we?
dimensionality is 1.
1. Why is the dimensionality 1? Because it's only. Yeah, explain. Dimensionality is 1 here?
Mm-hmm.
Why?
Fundamentally, this is a tool. So this is a tool because what you want to do is you want to do what you did over there. You want to go log of 10 is 1. Log
I see.
of 100.
So it's just a tool to get
is 2. But like
to math.
you can do this shit an infinite number of times, and this isn't very visual.
Right.
This is literally a tool to do this an infinite number of times.
To visualize.
And instead of this being in the numbers, these things just become x.
Yeah.
And so what you're plotting is x is just a number in one dimension, right?
Mm-hmm.
X is just a number
I see.
between
Yeah,
negative infinity
I got you.
and infinity, right? X is
Yeah.
just a single number, and what you're plotting here is a way to visualize the idea of taking x and running it through the log function,
Mm-hmm.
and it's a way to see, like, okay, if I take this number and run it through the log function, it becomes this number. If I take this number and run it through the log function, it becomes this number, and so on, right? It's a tool to see what happens when you run the x-axis through the log function, because then you get the y-axis once you run the x-axis through the log
So
function.
the x-axis is defining, by definition, the x-axis based off of log is defining the y-axis.
Exactly. That's the fundamental difference. And to put it very succinctly, down here, your observations are every single number on the x-axis. Up here, your observations are these individual points.
Right.
So you're only looking at 2 points here. Here you're looking at an infinite number of points.
I see. So one graph is designed to mapping the individual points that we have within space.
Mm-hmm.
The other graph is designed as a tool solely to get
To see a relationship.
Yeah.
To see a relationship between numbers and the function of those numbers.
I see.
Right? So, and given that, explain to me why this graph is fundamentally one-dimensional and this graph is fundamentally two-dimensional.
This graph is fundamentally one-dimensional because x is driving the entirety of it.
Exactly. Yeah.
So, like, where this, it's not x or y that's driving it, it's the points within space that are driving the graph.
Exactly. Yeah, you fucking got it. That's
Yeah.
exactly what it is. So, so that's another thing that is like kind of it's like should be obvious, but a lot of people look at those two things and they're like, oh, they're the same because it's two
Right.
axes.
Yeah.
They're not the same at all. This is a way to visualize every single one of these possible things all at once.
Yeah.
And this is a way to look at 2 points, each of which live in two-dimensional space.
I see.
Totally different things.
Yeah.
Now, it gets a little bit confusing because sometimes you do this kind of thing, where
This being our representation of a 3D graph.
where you can do this is x1, this is x2,
2, and then that's x3.
and then this is f of
Oh.
x1 and x2.
Interesting.
So
Why the functionality between those two?
let's just say that this is like a plane. This is kind of a shitty drawing. Imagine that this is like a flat plane here.
Yeah.
Why what?
So, why is the z-axis, why is the z-axis defined as f, which is a function of x1, x2, since we don't want to use y?
Think about it like this. Up here, what are the inputs to this function, and what's the input to this function? What type of object is the input to this function, and what type of object is the output to this function?
A numerical value of some sort.
Yep.
Yeah.
So a number goes in and a number goes out.
Right.
Here, what's the input to this function?
A point.
Mm-hmm. In how many dimensions?
Depends. Could be infinite.
Nope.
Is there no such thing as? I guess there can't be because it's solely data based. Theoretically, there could be infinite. Could it not?
Yeah. That gets into complicated shit. Let's not go there. we're staying at the basics.
Yeah. I see. So, two.
2 dimensions, exactly.
Yeah.
So what this is your points. Think about this plane. Now
This graph is literally, you take this plane and you make a third thing coming out of it called f of x, and that third thing is this performs the same function as this axis does here.
Oh, interesting. So it's
So-
performing a log.
Well, not necessarily a log. I said f,
Well,
so it could be any function.
Any function, like
But-
any base function that is defined for the comparison of the 2 points.
Mm-hmm. Just for reference in math, this you call this f that brings numbers in R2 to numbers in R1.
E2, R1. Okay.
Yeah. Because you take some point on this plane, boom, and then you say, I want the result of a function of whatever this function is. I want the result of that function, and what's the result of running that through the function? Let's give this function a name.
Yeah.
F of x1 and x2 is equal to, I don't know, 3x, oh actually this is going to be perfect, I know exactly where this is a good way of doing it, 3x1 plus 2x2.
Mm-hmm.
Okay, so that's this function. So what if we are 10 here, 10 here? What if we're at this point, which is the vector 5, 5? So we're going to start thinking of points as vectors now.
Okay.
Always. So now points are vectors. We're always going to call.
Yeah.
We're going to say the point is a vector like this.
Mhm.
So we go to the point. So our data now lives on this plane.
Right.
Okay. So how many dimensions are we at, by the way, here?
We're in 2 still.
Exactly. We're in 2 dimensions here. And this third axis is a tool. This third axis is a visualization tool to be able to understand this function f. This third axis is not an axis of.
Right.
It's not a
I
dimension
see.
axis.
So
it's a tool
it's
to
literally
see.
a tool to see the. How should I word this? So it's a tool to help you visualize or not visualize, but get data points depending on points that you have selected within this dimension.
Within the plane. Yeah. It's a tool that says if I take a point on a plane, I'm gonna and this function eats that point, it's gonna pop out a number.
Right.
And the number is gonna be the location on this axis.
There's obviously functions in which, so this is, you should correct me if I'm wrong, but there's obviously functions which allow you to also then compare points within that dimension.
What do you mean by compare points within that dimension?
So say you have, let's do it based off of the image, right?
Mhm.
Our image comparison.
Mhm.
So say we've unraveled our image. It's now pixel 1, pixel 2, all the way down.
Yeah.
And we have a library of those. So we have 100 images.
Okay. Yep.
We have 100 images, and they're all.
So
that
by the way,
same-
how many pixels are there total?
Let's just do 10.
Okay, and let's say we have 100 images.
100 images.
Okay, 10 pixels total?
Yeah.
So let's say they're like a 5x2 image each.
Yeah.
Okay, so what, by the way, how would you, so that's a data matrix.
Yeah.
Fill this in.
Uh.
So fill in what the data matrix is now. That you're talking about.
Yeah. Do you want me to do kind of like we did up here?
Yeah.
Okay. It would just be like, let's just do 1, 0, 0, 1, 1, 0, 0. Don't know why I did 4. 1, 0, 1. And so.
And then you can just say that there's some other,
Yeah, and then
there's
there's some other
image
values.
underneath it. Yeah.
Right.
And then, so this is x of r of what now? If you have, how many images did we say we had?
100.
And how many pixels are in each image?
10.
Okay, so what's this? Perfect. Exactly. Yep.
So times 100.
Yep,
That would be
so-
our matrix.
So X is a member of all of the set of all 10 by 100 matrices. is how you would think about the data matrix now.
Okay.
Where
That makes sense.
Yep. Cool. So anyway, go
And
on.
so say we have a function, right?
Mhm.
We have 100 images, and we want to run functions on these images.
Mhm.
So sometimes there's a compare function
Mhm.
to say, hey, we have 100 images.
Yeah.
Is there any duplicates within this data set? And so what you would do is you run a compare function
Mhm.
on these value sets, and you would do a loop through all. I don't know exactly how it would be, but you would have to obviously see every image.
Mhm.
So you'd have to do a comparison on each image
Mhm.
as it would run through. So you would use this F tool
Mhm.
within this space here to do a comparison on every point that is on this dimensional plane. Does that make sense? That's
So
what I was.
I see. So the comparison. So it's F and it eats two images.
Yes.
And what's the output of F?
The output of F would be like a bool. It'd be a true or false value. If it's the same image,
Mm-hmm.
it would be true.
Yeah.
If it's not the same image, it would be false.
I see. Okay. So that would be a function that maps.
And then you would have to compare by pixels. Like I'm not exactly sure how you would. There would be probably another function you'd write to validate it, but it would compare, right? It would compare the number set that you've given the image in the matrix.
Yeah. So that is interesting. I think that would be called a function F that maps R.
And you'd probably
2 by how many pixels? In each
10.
image? 2 by 10?
Yeah. Well,
R of 2 by 10 to the set 0, 1. So that's what that function would be. Because R is now a matrix that contains two images,
yeah.
and each of them have 10 pixels in them.
Right.
So you would organize it as a matrix with the first image being the first vector,
Mm-hmm.
the first row vector, the second image being the second row vector.
vector.
And it maps that matrix into the space, into the set 0, 1, where this is a discrete set.
I see.
So that's the function that you're talking about right
Yeah.
now.
Cool.
Yeah. So this is impossible to visualize.
Yeah.
But
I mean, I don't know if it's impossible if
yeah.
you keep the
Much
numbers
more,
low.
Yeah, you could.
But
Yeah.
But
But you
numbers
wouldn't
get crazy.
Sorry, it's impossible to visualize in this way,
yes.
right? But you would visualize it a different way in that
Yeah.
in that case, right? Like you just think about that the way it actually is, where you
Yeah.
think about two images and then you do something and
Right.
then you get
I mean, they'd
0,
still
1
be
as an output.
somewhere within this dimensional plane
Yeah.
in space.
Yeah.
It doesn't really matter where they are.
Yeah, but the point is you're right. What you're talking about fits into this framework that we're talking about, where this is a function from R2 to R1, and this is a function from R2 by 10 to
Yeah.
either 0 or 1, depending on
Right.
whether you're false or true.
Yeah.
So, okay. So, let's say that f of x1, x2, so f of a vector,
Mm-hmm.
right? So this now eats two-dimensional vectors,
Okay.
right? And in a matrix, say we have like a 3 by 2 matrix, right?
Mm-hmm.
Matrix the same X that we've been thinking about, where it's a data matrix, right?
Yeah.
With that, how would you think about passing every observation in that matrix through F? If you have a 3 by 2 matrix, tell me what's happening to that 3 by 2 matrix to
Can you
pass each observation through F.
say it one more time? I'll be honest with you. I'm getting to a point where like the
It's
brain's
getting,
starting.
it's
but
getting a lot.
say it one
Yeah.
more time.
Okay.
Because the brain's it's not getting a lot. It's just that after a period of time, like the brain gets fatigued.
Yeah.
And the brain's starting. It's a muscle, and the
Yeah.
brain's starting to get fatigued. That said, one more time.
Yeah. So
we have this housing data.
Yes.
Now it's just a matrix. But it's the same thing that's up here.
Yeah,
So
yeah, yeah.
54, 109, 69, 42.
Yep.
Remember that the way we're thinking about this matrix is here's the first data point, here's the
And
second
data point. Correct.
And remember, you could visualize this in a 2D plane where you put this as a single point in a 2D plane, this as a different single point in a 2D plane.
Right. Here's a question
Now-
for you, Alex.
Yeah.
Do those fit on the same dimension?
What is those?
The vectors.
These?
Yeah.
Yeah.
Okay.
This one is, remember here?
Yep.
And then this one
Is
like over here.
there. Okay.
Yeah, but these are just two vectors, each of them live on a plane.
Is there ever a time in which within ML when we're talking about vectors?
Mm-hmm.
So say currently, right, we have a list of 100 of these guys.
Mm-hmm. Yeah.
And the dimensions currently are 2.
Mm-hmm.
Is there ever a point in which you have a number, or not a number, but a vector that is like this? So vector 1, vector 2.
Yeah.
And say you have a list of 100 of them.
Mhm.
Is there ever a point, potentially,
Mm-hmm.
where that vector would have two numbers, say 1 and 2? Is there ever a point where this vector might not be on the same dimensional plane as all the other vectors that are of that same value set?
No, because think about it like this. Think about the two components of the vectors independently.
Mm-hmm.
This 54 lives on the entire infinite line of x1, right? So you go to
I'm moving it.
So you go to 54 in x1,
Okay.
and that's this component of it, right?
Mm-hmm.
But x1 is an infinite line.
Right.
It's negative infinity to infinity. So you know that this part of it can be any number between negative infinity and infinity.
Right.
Same thing with x2. This x2 goes from negative infinity to infinity. So this other number can be any number that lives from negative
right.
infinity
I
to
see.
infinity. So unless you've constricted your space in some way, put like a giant, like you can't go past this point,
Right.
then
They'll
any
always-
two-dimensional, so this plane is all vectors in
2 dimensions.
2 dimensions. This
I
is
see.
the entire plane of all two-dimensional space.
Okay. So so pretty much what it is unless you add some form of arbitrary valuation to it, it will always be on the same plane.
Yeah, these vectors, I mean, we're living in 2D space here.
Right.
Like, again, this whole setup here is a plane.
Yeah.
This axis is just a way to visualize what happens when you do something to one of the objects.
Yeah.
on that
I mean, that I'm not arguing. I'm just
Yeah.
interested to know, like, because it's good to know that there will never be a time or a case in which a vector, even though it potentially has the same dimensionality
Mhm.
as others,
Mhm.
right? For example, we did our 1 and our 2.
Mhm.
It's good to know that there will never be a time in which a vector that is of the same dimension
Mhm.
could potentially live in a different dimension, unless
Yeah.
you've added some arbitrary restrictions.
Yeah. Like if you say x2 can't be a number greater than 100,
Right.
well then, the number 101
Yeah.
doesn't live on that. But
Yeah. I just wanted to clarify that because I don't think we've, like, talking through this, we've defined it,
Mhm.
but I don't think we've actually clarified
Yeah.
that is always the case.
Yeah. So,
So what were you talking about before? Sorry.
yeah. Okay, so let's take this. So this is just one last. So this thing that we're going into right now, I think should probably be the last thing that we do because I think we're getting a bit tired now.
Yeah.
It's a lot of thinking.
A lot of thinking.
But this is going to have a punchline. This
Let's go get a
line of thought.
milkshake.
Yeah. This line of thought that we're about to go into is going to have a punchline. So.
Okay.
And that punchline is going to be great because it'll lead us into thinking about vectors and dot products and thinking about linear algebra.
Sounds like a good fucking time.
All right, so let's say our function is f of x1, comma x2 equals 3x1 plus 2x2. So first of all, let's just think about that function. What's that function? What type of objects does that function eat, and what type of objects does that function spit out?
This function eats two vectors.
Two.
One-
What do you mean? Two vectors, or what do you mean by two vectors? What's x1?
2 points within space.
Yep. One.
No.
What's x1?
X1 will be some arbitrary number within, well, it'll be this. So it'll be some arbitrary number within our rows, those are columns, within our cols. And so depending on what number was in our cols,
Yeah.
we would put in here. So if it's x1, for example, this would be 54, and then this would be 109.
Okay.
And then that would be 3 times 54 plus 2 times
Close the
109.
parentheses.
Oh, did I not? Sorry. 109.
Yeah.
What is that? Not to, is that the power 2? Is that what you're defining there? What is this? What's this guy?
Oh, this is just 3 of x1.
Oh,
plus
this is
2 of
x2.
x2.
I
Yeah,
see.
That's x. That's the dimension.
Yeah. Sorry. I had brain fart.
That's just the dimension.
Yeah.
It's just
So
a rotation.
this is what it would be. And then that would be our vector.
Perfect. Well, vector. What is this? What is this object? What type of
Oh,
object?
this is a function.
Well, no, this object here. The result of these calculations. What type of object is that?
I mean, it's the sum of. I'm not sure.
Think of this like R thing. What type of?
It's a real number.
Yeah. That's
Yeah.
all I wanted. It's
It's a real
so
number.
so this so
So it's an
here's-
output of a real number.
here's something that's really cool. And I'm going to introduce you in math. There's this concept of duality.
Okay.
These little stars.
Yeah.
Say that duality is a cool idea. There's two ways of thinking about this function. Either this is a function that eats two numbers. So moving you back. So you can either think of this as a function that takes two objects, two numbers in R1,
Okay.
your x1 number and your x2 number, and outputs just another number.
Okay.
Or you can think of it as a function that takes one object
So there's this duality idea where either x1, x2 is two different numbers,
Or if they're one.
or it's clumped together into just it's a single object, and that object is just a point in two-dimensional space.
I like the second. That's fun.
Thinking of it as a point in two-dimensional
Yeah,
space.
That's fun.
But like, it's the same
Same
thing.
thing,
It's just a different
yeah.
way of thinking about it.
Yeah.
A lot of math is just that. A lot of math is, like, actually most math is just taking two things that are the same, but you think about it in a different way.
Right.
And so there's two ways of understanding this, right? It's either you take a longitude and you take a latitude. You think of those as separate beings, and you
Yeah.
combine them together in some way to create one result.
Or you think
of
a single.
a single location on Earth,
Right.
and it's that location's temperature or something,
Yes.
right?
That's fun. That's actually when you're doing point cloud.
Mm-hmm.
That's kind of how that's set up.
Yeah.
So it's really cool.
So here is the kicker. Here's the punchline that I wanted to end with.
Okay.
There's a very particular reason why I chose this function instead of like a logarithm or an exponent or something like that.
Mm-hmm.
Why I chose 3x1 plus 2x2.
Okay.
Here's the reason why I chose that. Do you know how a dot product is defined?
No, it's been forever.
A dot product is defined as, I'll just do this. 3x1 plus 2x2 is the same thing as the vector 3, 2
Times
dot producted with the vector x1,
x2.
x2 equals f of x1, x2.
So is a dot product just multiplication?
A dot product is you take the first element of this, you multiply it by the first element of this, and then
Right.
you take this first element of this, multiply it by this, and then you sum all of those together.
Interesting.
That's the dot product, and this is why I wanted to end here. The dot product is the fundamental operation in all of linear algebra, and it pops up everywhere. It is by far the most common operation that exists in all of math by a large margin. The whole reason that GPUs are used in machine learning and why everyone goes crazy over compute and why everyone tries to optimize matrix operations is because they're trying to get the dot product operation to be able to occur as quickly as possible.
I see.
Because almost all machine learning under the hood is built on top of using the dot product in different ways. So what we're going to do in the future is we're going to spend a lot of time thinking about dot products and thinking about what the operation of the dot product is doing. There's multiple ways to understand it. Matrix multiplication is literally just doing a bunch of dot products. The dot product is related to norms. It's related to everything. Everything is built on the dot product in linear algebra. It is the fundamental operation of linear algebra.
Yeah.
So this idea, 3x1 plus 2x2, is the dot product of the vector 3, 2 and the vector x1, x2. And so that, and then I just want to leave on one note, which is that we're starting to bring in the same idea that we said over here of A, B, right? One of them is the operator, one of them is the object.
Right.
Because over here, the dot product is kind of like a, it's kind of like multiplication in that way. Like here, you can think of the vector 3, 2 as being a function that acts on the vector x1, x2.
Okay.
Or if we gave like numbers to this or whatever.
Yeah.
Right, we could think of x1, x2 as being a function that acts on 3, 2.
Right.
And in the same way that multiplication works the way it did that we talked about before,
dot products, you can think of it the same thing. That's the idea of duality, where you think about one thing as being the function and the other thing as being the vector, but that ends up being the same thing as thinking about the other thing being the function and the first thing being the vector.
Yeah.
You can switch the way that you think about it arbitrarily and it's going to produce the same result. That's going to lead into thinking about the row space of a matrix and the column space of a matrix. That's going to lead into thinking about, with the matrix AB, thinking about the first thing as the operator versus the second thing as an operator.
Yeah. So this operation here is just a dot product,
And everything is built on dot products. So,
Dope.
yeah, that's what we'll end on.
Cool. All right.
Sick. I feel like you learned a ton. How do you feel?
I feel tired.
yeah.
I feel smart.
Yeah.
Smarter.
Yeah.
You know what's gonna make it even better?
What?
Ice cream.
Hell yeah.
Did you hear that? It's time for fucking ice cream.
Yeah.
Ice cream!
Hell yeah.
Okay. Goodbye.